you're going to be asked to figure out the velocity of a wave. Okay. And there's two different methods you can have here. Okay. If you know the distance the wave travels and the time to travel, then we just use velocity as distance over time. Okay. Because, key point, guys, this makes life easy too. Always assume the wave moves at a constant velocity. Does not accelerate. So if you got the distance divided by the time, you can figure it out that way. So if they gave you the fact that, hey, you know, we get these waves, and I know that by the time five of these make it a certain distance. So if we took this as say 100 meters, from this, for this wave to go from here to here, and the time was 20 seconds. Okay, you can do the math pretty quick there. This thing's going to travel 5 meters every second, assuming we look at like the first wave and we want to know over time how far that goes. That's how you would do it with distance and time. However, if they don't give you that, but they tell you, if they give you the frequency of the source, so how many waves per second are being created, and they tell you the wavelength, there's what's called the universal wave equation. And it says, this always works, always, is that the velocity of a wave can also be calculated by multiplying the wavelength of that wave by the frequency of the wave source. So this is where I want to bring this in. Wavelength, the unit is meters. Remember, frequency is hertz, and hertz is 1/seconds. So the unit here is still meters per second. But now, you have two different ways to define this. So if I said this was a 20 hertz source, a very low, like 20 cycles per second, and the wavelength, the spacing between crests was 10 meters. Just plug and chug, guys. 10 meters, 20 per second. Okay, this thing's going to boogie along at 200 meters a second. Some of the problems are going to ask you to figure it out both ways. So kind of be mindful of that as you're looking at this. Okay guys, welcome back. I want to give you a couple of example problems based off of where we finished the first part, and then we'll look at some more particulars about the behavior of waves. Now in the first one I have a 200 hertz source is producing waves, and the waves have a 3 meter long wavelength. And they're going to ask you, like, what is the velocity, what is the speed, how fast is the wave traveling? So first thing you got to see is that that's your frequency. It's in the correct units of hertz, and that is your wavelength. They're in the correct units, so if you want to know the velocity of the wave, you write down that equation, the universal wave equation, and we're going to have a 3 meter long wavelength, and we have 200 hertz, which is 200 waves per second. So 600 meters per second is the velocity of that wave. And again, it's a constant velocity. If you looked at this and tried to use the other equation, velocity is distance over time, we don't have any of that here. Okay, that's not a distance that we look at. We look at how far a wave would travel. So that's one type of problem. We use the universal wave equation. The second one is an echo type problem. Like you'll see like a sonar, someone's shouting toward a cliff, and they're going to ask you something about either how far away the object is it reflects, or the total time to hear the echo, things like that. So in this problem, you have a person standing at some distance away from a cliff. He hears his echo 5 seconds later. How far away is the cliff? Well, the first thing you have to keep in mind, if they're shouting towards a cliff, the velocity of sound in air is 343 meters a second. It's a little under a quarter mile a second. So in 4 seconds, the thing's traveling about a mile roughly. So that's a number you should know, 343 meters a second, speed of sound, or velocity of sound in air. You need to do that to do this, otherwise you're stuck. So what you want to do is think about what's happening here. Any kind of an echo is going to involve a round trip. So what that's going to mean is when he shouts, his voice is traveling out to a distance d away from the cliff, and then the echo is going to come back. It's that same distance. So this is the whole round trip right here. Now, the round trip distance is 2 times the distance to the cliff, and the round trip time is your total time. Which is 5 seconds. So if we use the basic velocity or constant velocity equation, and velocity is distance over time, we're going to solve for how far away the cliff is. So keep this in mind. We have everything in terms of the total distance and total time. So keep in mind that what's actually happening in this equation is we really have this going on. We have the velocity of the sound, the distance, the total distance the echo travels is 2 times the distance to the cliff, and the total time is 5 seconds. Okay. If you want to cut your work in half, you use 2.5 seconds, and that's the time it takes just to get to the cliff. But this is the total round trip. It's going to be the same because you're doubling both things. So if you have 343 meters a second, and that equals 2 times d over 5, you'll be able to cross multiply that. So 343 times 5 over 2, and that'll be your distance. Roughly what you're looking at here is if sound travels about 340 meters a second, and it's going to take 2.5 seconds, your 2.5 times 340, that's going to give you a rough number of how far away the cliff is. So you might see a problem like this where they have, say, a submarine trying to echolocate to an undersea cliff, or a boat trying to find some fish. You're going to read it as an echo problem. You're going to see the difference between these two. But these are two that you're going to encounter as you start to problem solve. So that's some example problems right there. Just remember to show the equation you're using, the list, all that kind of stuff.